Hi, Mick McQuaid here, welcoming you to day 16 of iste780, data-driven knowledge discovery. And today we have a lab on decision trees. So let's get started. I've already turned on R here, and I've already got my commands typed into my text editor. So let's execute them. So the first thing that we're going to do is probably have to download the tree library, which I've already done. There are about four libraries I think you have to download for this. Be sure when you download packages that you get that you check the install dependencies. One of the packages today has a dependency. Okay, and then from the ISLR package, we're going to take the car seats data, and if you recall, the car seats data contains the names. Oh, what am I saying? It contains the names. It contains information about the sales of car seats, and the outcome, the response variable, is sales, and the predictor variables are things like price and shelf location, and this is an example of a regression problem because sales is a quantitative variable. So what we'll do to do a classification tree from this is convert it to a qualitative variable, and that qualitative variable is going to just be high, or were the sales high. If the sales are 9 or higher, then we'll call them high. So this if then else statement simply takes this as the condition. The condition is sales less than or equal to 8. If that condition is true, then the value of high is no. If that condition is false, then the value of high is yes. And so we can just use no and yes now to split the tree. Okay, and then we're going to add this new column high. So this is now a column that has the same number of rows as all the other columns in car seats. So we're just going to add that to car seats, and then compute a classification tree using all of the data except for sales, obviously, since sales is the original response variable. So here we're cutting out sales by saying minus sales. We're saying take high and predict high based on everything except sales from the car seats data. And a summary of this tree shows that this is a classification tree. You can see that we've used the variables that we've actually used is, let's see, 6, 7, 8. So we've used a total of 8 variables. If you look at the original data, there are 11 variables. Of course, sales is a response variable, so there are really 10 predictors. And of those 10 predictors, we've used 8 in this model. And we have 27 terminal nodes. And our misclassification rate is 9%. Okay, now we can plot this, and this is going to be a two-step plotting procedure. So in the first step, and this is using a plot function that's internal to the tree library. So as is typically the case when we do plotting, the plot function will first look at the object that we're plotting and see if it has its own method, which this one does. Now I said that this is a two-step method because the second step is to put the actual text on the nodes. And this pretty equals 0 simply prevents any of this stuff from being abbreviated. And it seems to me I had to go up to pretty equals 4 before I got any abbreviations at all. And I haven't tested how high I need to get pretty to make it what you might call truly pretty. Okay, now this same information that's in this tree, so this tree the root of the tree is split at shelf location. That's the first variable that splits us. and price is the second one. So that makes a lot of intuitive sense that shelf location and price would be the two most important variables. And all the information that's in this tree is also available just by looking at the object itself. So if I just name the object, I'll get over here a copy of the object. And it's got this same information. So we have plus a little bit of quantitative information. So we see that shelf location is the first variable on which there's a split. Price is the second variable on which there is a split. And we see this information in greater detail than we saw it in the graphical depiction of the tree. But of course, the graphical depiction of the tree is easier to read at a glance. Also, if you expand this to fill your entire monitor, you'll find it a lot easier to read, assuming that you have a large monitor. You can also, by the way, there are other things that you can do to make this more readable. For example, when I expand this to my entire monitor, if I then save it to a PDF or a PNG file, it maintains that aspect ratio, so that if I shrink it back to this size, all the letters and numbers are shrunk to a more appropriate size. So, and I can also use the CEX option in plotting to change the size of the characters. So there are a number of things I can do to make it more readable, but I'm not going to do that right now. I'm just going to push on here. And now let's estimate the test error. So we need to create a training set and I'm doing set seed so that we match the textbook output, and creating a training set and creating a test set. And a high test. So now I run this again using the training subset to build the model, and then I use the model that I've built with the training set to test on the test data. And then I take a table of the results, and what I see down here is no, these are the ones that we correctly predicted to be no, that's 86. And then yes are the ones that we correctly predicted to be yes, that's 57. So and there are a total of 200 observations here. So the fraction that we've done, fraction of correct predictions is 86 plus 57 divided by 200, which is a fraction of 71.5%. Okay, now how big a tree should we make? You know, is really this 27 node tree that we have here optimal? I'll say set seed to match the textbook output and use cross validation. And let's see, what did I make? I made a little note here. Prune misclass means to use classification error rate instead of default deviance. So in fact, where it says dev here, this is actually the classification error rate. And K here, it means the same thing as alpha in the textbook. So when we studied this in the textbook, we used the term alpha to mean what R uses K to mean. So let's take a look at the cross-validation object here. And the key thing here to look at is the classification error rate, which is listed under dev here. And what we want to do is find the lowest value, where our error rate was the lowest. And we can see that our error rate was the lowest here at 50. That's 1, 2, 3, 4, 5. So the size of the tree that's associated with the lowest error rate would be 1, 2, 3, 4, 5, the tree with 9 nodes. And that has an alpha of 1, 2, 3, 4, 5 of 1.75. Okay, so now we'll plot the error rate on a two-panel plot. So par is going to make a matrix of plots, and the matrix is going to be one row by two columns of plots. And by the way, par also shut off input to this by default. Par shuts off input to the previous plot. So now anything we do is going to overwrite the previous plot instead of adding to it. Okay, so the first thing that we're going to do here is to plot classification error rate by size. So as expected, the classification error rate is lowest when the size is 9. That's what we saw in this information here. And now we'll find alpha, and I believe our lowest alpha was 1.75, which is a little bit harder to see in this depiction. Okay, so now let's prune the tree to the best subtree. So the best subtree had 9 nodes, so we can prune it using the prune function, and we can plot it. It has its own internal plot because it's a classification tree, and we can stick the text on there. So this is what the optimal subtree looks like. And so then we can test the optimal tree and see how good a job does it do on the test data. So we've created it using training data, and now we're testing it with the test data, and we get this. We did 94 no's that were really no and 60 yeses that were really yeses. So our correct classification is 77%. So it's an improvement over what we did with the full tree. So that's a pretty nice deal, isn't it? Now let's suppose that we do a larger tree just to prove that it's going to be worse. I hope it's going to be worse. Let's plot that. And let's test it. So let's just look at them. So this is a bit bigger, and we're going to test it using. I'm using the exact same commands that I used before, and here we get we get worse. So it's 74%. So the 15 node tree is we got 86 no's we predicted correctly, and 62 yeses we predicted correctly for 74% correct classification rate versus 77% for the 9-node tree. All right, now we'll move on to regression trees. And we're going to use the Boston data set, which is in the mass package for this. If you recall, the Boston data set is on home values, median home values is the output variable here. So we're going to create a training set and a test set for this. No, we just created a training set, sorry. We didn't create the test set yet. And so here's our regression tree. And we've only used 3 variables here. So let's see, what are the variables in Boston? Wow, there are a lot. So we only use 3 of them, LSTAT, RM, and DIS. All right, let's plot this tree. So it's going to be a small tree. It's only got three variables in it. And we'll see how we're reusing these variables for different levels of them. Now, why did I plot the tree again? Oh, I just did it to test different values of pretty, and pretty 0 and pretty 1 don't make any difference here. Pretty, eventually at a higher level of pretty, you'll get abbreviations, but these are already pretty abbreviated. Okay, so now we're going to try pruning. And what this is telling me is that the the cross-validation says that the best values that I'm getting are for the largest tree, so the 8-node tree or 7-node tree, for that matter, is the best. So, but we're going to prune it anyway. We're going to prune to 5, just because we need exercise in pruning. Okay, so there's the pruned set, pruned to 5. Just got 2 variables now. And but because the cross-validation said not to prune, let's try the entire tree on the test data. So let's take, and rather than creating test data, we're just saying Boston minus train. So that's just going to give us everything else as the test data. So that's giving us our prediction. Our prediction object. And an AB line through it. And the mean test MSE is 25, and that means that the root MSE is about 5, and that corresponds to standard deviation. So the 5 is in units, in the same units that the original data is in, and the original data was in thousands of dollars for median home value. So this is telling us that our predictions from this model are within 5,000 US dollars of the true median home value for the suburb. Okay, now we move on to bagging and random forests. So we need to download the random forest package for this, to use this both for bagging and random forests. And one really neat thing about random forest is it depends on the R color brewer package. Unfortunately, we're not actually going to use the R color brewer package in this exercise, but that is one of the R packages, one of my favorite R packages, one of the packages that I would most like you to familiarize yourself with if you have time. If we had extra time in this class, that's one of the packages that I would play with. R color brewer makes your plots colorful, but in a very special way. It's based on psychometric research into how people perceive colors and quantities, so that people who look at plots done with the R color brewer colors are better able to answer quick factual questions about the data. And this has been extensively studied by the inventor of color brewer, whose name is Rebecca Brewer, who's a professor, I think, at Penn State or someplace. And you can just, if you Google color brewer, you can find out more about that package. So I recommend that to you, even though we don't really have time to go into it here. We're just going to do the exercise or do the lab. So we're going to load the random forest package, and then we're first going to do bagging with it. And the way that we do bagging with it is we use the random forest function, and we set m equal to p. So this is, so m try is what we learned as m in the textbook. P, of course, is the number of dimensions. And did we look at the did we already look at the names in here? Yeah, 8, 9, 10, 11, 12, 13, 14, including the response variables. So 13 is the number of predictor variables. So by setting m equal to p, we're doing bagging. If we set it to the square root of p, or the integer closest to the square root of p, then we would be doing a random forest. All right, let's take a look at the bag object. And there it is. And let's try it on the test data. Again, we don't explicitly create a test data set. We simply refer to the portion of the Boston set that's not in the training subset. And we plot the fitted values and an AB line through them and check the mean of this. And wow, the mean is way lower, way lower. Remember the root MSE, I mean the MSE was 25 for an individual wait. No, the optimally pruned tree, that was it. Yeah, the optimally pruned tree. So bagging did a much better job than the optimally pruned tree. That was where we got the 25. Okay, so now let's try specifying the number of trees as 25. And the mean is very similar there. Okay, now, and by the way, it may be slightly higher or slightly lower when you do this. Did I set seed for this? I'm not sure. I don't remember. My results are slightly different from the textbooks anyway. Okay, so now let's try a random forest by reducing the size of m. So instead of m equals p, we're going to have m be some smaller value, which I've forgotten. Yeah, so that's not quite the integer closest to the square root, is it? What would be the integer closest to the square root would be 4, I think, in this case. But anyway, we're using a considerably smaller value of m here. So this is a random forest, and our guess is going to be that it's going to perform better or worse than bagging. What is your guess? Think about that for a second before I push the button. And if you guessed that it would be smaller, you're correct. So a random forest, we expect to perform better than bagging. Now, one of the problems that we talked about was the difficulty of interpretability of random forests, or of bagging for that matter. So one of the functions that's supplied in the random forest library is the importance function. So we can use the importance function to find out what which items seem to be of the greatest importance, and we can also plot this. So there's a special plot for this, and this plot will make it much easier to see. Reading this list, you have to read down the list until you figure out that 31 and 27 here, and 69, 27, and 6705. So there are these two different measures of variable importance here. And we've plotted these two different measures of variable importance. And I included a little note here about what they are. So INC MSE is the mean decrease of accuracy in predictions on the out-of-bag samples when the given variable is excluded from the model. So this is how much worse things are when we don't use this model. I mean, when we don't use this variable in the model. And INC node purity measures the decrease in node impurity. So this is how valuable it is when we do splits, how much of a difference it makes when we do splits using that variable averaged over all the trees. And it can be used for a regression tree or a classification tree using RSS as the value of node impurity for a regression tree, and using deviance as the measure of node impurity for a classification tree. Okay, and the result that we see in both of these cases is that RM and LSTAT are by far the most important variables. So that aids in interpretability for if we're going to do random forests or bagging, we need to make some allowances for that. Okay, now the next thing that we'll try is boosting, and next and last thing, I guess I should say, that we'll try is boosting. So we're going to use a different library for that. GBM, we're going to have to download that package. By the way, these, I'm making these recordings before the course has officially started, and I'm just using whatever is the latest version of the packages that I download them just before I do the lab. So hopefully I'll catch any bugs that exist. But it's possible that there'll be a new version of any of these packages. I mean, one of the nice things about open source software is that people just submit new versions whenever they feel like it. So you may get slightly different results or have slightly different problems, have slightly different bugs than what I experience. And that's okay. I don't think that's a really major problem. Okay, so we're going to do boosting here on the Boston training data. 5,000 trees, and here's a summary of the object. And the summary of the object both shows us the summary of the object in the terminal and also graphically. So here's a graphical version of it, and you can see here that LSTAT is the most important. This second one, although the labels are only every other one, the second one is RM, and you can tell that by looking at the terminal version where you see that LSTAT has 45 and RM has 43. So let's and we can also do so this is a plot for all the variables. We can do partial dependence plots for LSTAT and RM. So we'll do one here for and we redid par, even though we're using the same type of thing, in order to get rid of that, so we get the two partial plots side by side. That's really the only reason to do it that way. Okay, so we now have partial dependence plots just for these two. Now, we have created the model using the training set, so once again we need to test it on the test data. And once again, we want to find the test MSE, and it's lower. It's quite good. So it's at least as good as the random forest. I think that was in the 11s also. Now we did the default. Oh, it says it's similar to random forest and superior to bagging. Okay, so I believe that because I wrote that earlier. Okay, so try boosting with lambda equals 0.2. So I guess I should point out that the default value of lambda here, I thought I made a note of this. The default value of lambda is higher, is much lower than this. And so trying it with a different value, let's see what kind of difference that makes. So we've created it. Now we test it. Now we find the test MSE. And the test MSE is lower. So lambda 0.2, oh, here's where it says lambda 0.2 gives a slightly lower test MSE than the default of lambda equals 0.001. And that's it. That's the end of this lab. Thank you for your attention. And I look forward to going over the next to last chapter, and the sexiest chapter, by the way. So look forward to tomorrow. We'll talk about support vector machines, which I think is, I'm sure at least some of you will agree, is the most interesting technique that we'll study the whole term. Thanks again.